is going to fall. And we talked about this when we talked about the respiratory system. If we see a low pH and it's associated with the opposite, a high CO2, we know that this is a respiratory acidosis. Now, our peripheral and central chemoreceptors are going to sense a drop in pH, and that's going to try to stimulate or drive ventilation. So hopefully we can begin to blow off that excess CO2. Okay. But in terms of acid-base balance, this principle is going to come in handy, and we'll talk about this probably next class, how we clinically use the principle. A normal in your handout is your normal blood gas values. Okay? When we draw blood gases, the blood gases, the results are going to tell us the pH of the blood, the PCO2. When we use a lowercase a, it refers to arterial blood, so the partial pressure of CO2 within the arterial blood. The PO2, it's going to provide the bicarb concentration, and it's going to provide the hemoglobin saturation. Okay. And you have the normal values here within your handout. Again, a normal value for pH is 7.35 to 7.45. If you had to hang your hat on any number, it would be 7.4. For PCO2, your normal values are 35 to 45 millimeters of mercury. The number right in the middle is 40. PO2, 80 to 100 millimeters of mercury. Bicarb is going to vary somewhat depending upon the lab, but typical numbers are like 22 to 26 milliequivalents per liter. Remember that when we talk about electrolytes, we use milliequivalents. And in terms of hemoglobin or oxygen saturation, typically it's going to be, what did we tell you? 95%. It's going to be nearly fully saturated. That's related to that oxyhemoglobin association curve. Okay. Now I want to see where we catch up here. Okay, we're here now. Okay. Now, so these are normal values. It turns out that we ordinarily, let me go back. Yeah, I gave you these, okay. We normally bombard our bloodstream with acids. How does that occur? Well, when pharmaceutical companies produce drugs, for instance, most drugs are designed to be either a weak acid or weak base. For instance, the example I'm giving here is aspirin. It's salicylic acid. So that when it's absorbed into the bloodstream, what does it do? What do all acids do? What's the definition of an acid? Yeah, it's a hydrogen ion donor. So these acids release hydrogen ions into the bloodstream. Okay? That'll have a tendency to do what in terms of pH? Drops the pH. Okay? Ingestion of foods or beverages like alcohol. As these foods and drugs are metabolized, oftentimes you produce acids. Like alcohol is converted to acetic acid, which when enters in the bloodstream, it releases hydrogen. Okay? As a result of metabolism, we produce acids. You know already that as a result of anaerobic metabolism, you produce lactic acid. Okay, that's released into the bloodstream and releases hydrogen. When proteins are metabolized, many proteins contain phosphate-containing groups, so it leads to production of phosphoric acid. When you break down fats, you produce fatty acids, keto acids. They release hydrogen. Okay? And then you know that CO2, we showed that equation, that respiratory equation, can be converted to hydrogen. So I think of that as kind of a respiratory acid. So the point I'm getting at is we're constantly bombarding our bloodstream with acids. How is it then that we maintain a fairly stable pH between 7.35 and 7.45? The answer is buffer systems. There are buffering systems within the bloodstream and within the body that tend to preserve a stable pH, that tend to oppose a deviation in pH, so that if our pH attempts to fall below 7.35, these buffering systems kick in. Or if our pH tends to want to climb above 7.45, these buffering systems kick in. And in doing so, they tend to oppose any shift in pH. Okay? Now, there are three different buffering systems. There are chemical buffers. These are molecules that are present within the bloodstream that oppose any shift in pH. These chemical buffers act within seconds to resist the pH change. So they act the quickest, but these aren't necessarily the strongest of the buffering systems. In fact, as we go down this list, we'll go from quickest to slowest, but also from the weakest to the most potent. Okay? So in addition to the chemical buffering system, the respiratory system helps to buffer pH. Okay? The brainstem can alter the rate and depth of respiration within a matter of minutes to compensate for an acidosis or an alkalosis. Okay? For instance, let's look back at our equation. Okay. Let's suppose that someone's in diabetic ketoacidosis. Okay? Meaning that the pH of their blood is now below 7.35. And it's below 7.35 is because they have too many keto acids that are releasing hydrogen. So the hydrogen ion concentration within the blood is increasing. Okay? Which means the pH is falling. Okay? So two things happen. When you have an increase in substrate on one side of an equation in equilibrium, in order to reestablish equilibrium, this increase in substrate is going to drive this equation from right to left. This is Le Chatelier's principle. So that hydrogen is going to be consumed by reacting with bicarb, producing carbonic acid. And then in turn, carbonic acid is going to dissociate into CO2 and water. And you will say, well, won't that cause a buildup in CO2? No, because the drop in pH at the same time is going to activate that respiratory reflex where we begin to hyperventilate. And so as we produce more CO2, what happens? It gets excreted through the lungs. We blow it off. Okay? So by consuming this excess hydrogen, what happens to the pH? It begins to climb back up toward normal. This is an example of respiratory buffering. Okay? That's why anytime a patient with DKA comes into the ER, they may be comatose, but they're hyperventilating. Okay? It's their body's response to the acidosis. It's those chemoreceptors in action. Now, that's a more potent buffering system than the chemical buffers. Finally, the third buffering mechanism is within the kidneys. Okay? This is the most potent buffering mechanism, but it requires the longest to kick in. It requires hours or sometimes days to kick in. Okay. In the face of, for instance, a severe acidosis, what do the kidneys do? They secrete more hydrogen and they reabsorb more bicarb. Bicarb is going to be available to do what? To buffer that excess hydrogen. So in the face of acidosis, the kidneys secrete more hydrogen, reabsorb more bicarb, and those two actions are going to bring the pH closer back toward normal. Of course, in the face of an alkalosis, what do kidneys do? They secrete less hydrogen. They hold on to hydrogen. And they reabsorb less bicarb. So they're excreting more bicarb, so you have less buffering capacity. That's good because you want to hold on to hydrogen. You want to, in the face of an alkalosis, if you hold on to more hydrogen and get rid of more bicarb, you're going to bring the pH down. So in the face of an acid-base disturbance, there's a tendency for these buffering mechanisms to kick in an effort to maintain homeostasis. Because you know, if you come in with DKA and your pH is below 7, there's a good chance you're not going to make it, that you're a gone McCon. Okay? Why? Because all of these enzymes that are part and parcel of metabolism, metabolic reactions, they all function optimally at a pH that's close to 7.4. Okay? And in fact, what happens is as the pH becomes progressively more acidic, these enzymes, which are proteins, begin to unfold or denature. And then what happens? They can't catalyze metabolic reactions. Why? Because the enzymes, they bind to substrates like a lock and key. They have a specific configuration that's required for them to bind to substrates and accelerate a chemical reaction. If these enzymes unfold, they lose that three-dimensional configuration and can no longer bind. They can no longer accelerate chemical reactions. Okay. Are we okay now? Are we in? Okay. So let's talk about chemical buffers. A chemical buffer is a system of one or two molecules that acts to resist changes in pH when a strong acid or base is added to the bloodstream. And there are lots of different chemical buffers, the most important of which is the bicarb buffering system. There's a phosphate, there's a protein buffer system. There's lots of buffering systems. The most important, and the one we'll use as an example, is the bicarb. But first we have to define what a strong acid is versus what a weak acid is. Hydrochloric acid is a strong acid. If I take 10 molecules of hydrochloric acid and I dump those 10 molecules into water, a strong acid is going to undergo near complete dissolution. In other words, all 10 of those molecules are going to dissociate, releasing free hydrogen. So you're going to have 10 free hydrogen ions floating around within that water. Okay? And you'll also have chloride, but it won't be associated with hydrogen anymore. It'll be dissociated. And so that's going to result in a significant drop in pH as the hydrogen ion concentration goes up. On the other hand, let's look at what happens with a weak acid. Carbonic acid is a weak acid. If I dump 10 molecules of carbonic acid into this beaker of water, most of the molecules are going to remain undissociated. Let's say one or two of them dissociate into hydrogen and bicarb. Okay? But the rest of them don't. Are you going to have as marked a drop in pH when you dump an equal quantity of bicarb into the solution? Of carbonic acid? No, because it's not going to undergo complete dissolution. It may only release 2 ions of hydrogen, whereas in this one, with complete dissolution, we release 10. So with a weak acid, when it releases free hydrogen, it doesn't do it near to the extent of a strong acid. And so it won't result in as significant a change in pH. Is that clear?
Uh-huh.
Okay, so let's go forward. So let's suppose, now, the bicarbonate buffer system is really 2 molecules that exist in equilibrium within the bloodstream. It's really carbonic acid in equilibrium with sodium bicarbonate. Okay? One of these is a weak acid. That's carbonic acid. One of them is kind of a weak base. Now, if I dump hydrochloric acid, a strong acid, into the bloodstream containing this buffering system, what's going to happen is the hydrochloric acid, which is a hydrogen donor, is going to react with the sodium bicarbonate, this weak base. A base is a hydrogen ion acceptor. So sodium bicarbonate is going to pick up the hydrogen that's being released, and it's going to be converted to carbonic acid. At the same time, the chloride is going to link up with the sodium here and simply become salt, so it's chloride. Now, what we've done as a result of this interaction with the buffer is we've converted a strong acid into a weak acid. Will there be a change in pH? Yes. But this weak acid doesn't dissociate near to the same extent as the strong acid would. So, whereas if there were not a buffer available, we would have a marked drop in pH. By converting the strong acid to a weak acid, the drop in pH is not going to be near as severe. In other words, we're buffering or blunting any drop in pH that would otherwise occur. So by converting strong acid to a weak acid, we're reducing the amount of free hydrogen that's released into the blood. We're buffering any drop in pH. Now, what if we had a strong base? A strong base, the example we're going to use is sodium hydroxide. Sodium hydroxide completely dissociates in solution, releasing free hydroxide ions. Okay? And each one of these is going to bind to hydrogen. Okay? In fact, when hydroxide binds to hydrogen, it produces water. But in doing so, it's removing free hydrogen from the bloodstream, or from whatever solution it's in. And so it's going to cause an increase in pH. Okay? And remember, our body doesn't like changes in pH. So if we dump a strong base, like sodium hydroxide, into our bloodstream, that strong base is going to react with this weak acid, carbonic acid. Okay? It's going to pick up this hydrogen from the acid